Okay, we are looking at a sample problem. I did this right before I started the video. I launched a small toy car off the side of the thing, and it landed. Say 6.5, right? 6.5 feet from from the ledge, and we said that the ledge is 86.8 centimeters high. And the question is, how fast does the car leave that particular ledge? Okay. If you would like to, I let them have some time to kind of start setting this up. If you want to pause real quick and unpause to see kind of the video, we're going to go over it right now. So pause, and now I go explaining. All right. So what's the car going to do? Well, I launched it like this, yes, horizontally. What path is it going to take? Thank you. Sound effects are always welcome. Always. Okay? Thank you. All right? If I laugh, I want you to know right now, it is never at you. It is with you. And if you're not laughing, you're doing it wrong. Okay. So, very importantly, we said that this is going horizontally, which very much matters in your givens here in just a second. Okay? This vector right here, I'm going to try to visually demonstrate where certain math ideas are coming from. But this vector right here is in total our velocity initial, right there. Okay? Our velocity final, well, you kind of can get a gist of this, but which way is the car going to go into the ground? Kind of down and to the right. Yes? Maybe not exactly, but something like down like that. Yes? That is velocity final. Okay? Now, while it curves, please understand, using another color here, let's go with a lighter pink. Its displacement doesn't curve. When we do it in math, displacement is starting at from the start position to the final position right there. Okay? Now, we don't usually, in two-dimensional kinematics, care about that vector. We usually care about its components. I told you on Friday that this guy is delta S. But in truth, I don't really care about delta S because usually nobody asks about it. What they ask about is its components. This component of that vector is, of course, known as delta y. And this vector of that component is delta x. What I'm attempting to do right now is separate for you. Yes, it will take a parabolic shape. We'll talk more about why it's going to take a parabolic shape a little bit later in this chapter. But these arrows don't necessarily go with the curve. They go with that vector. We just don't usually worry about it. All right. So now let's talk about how you're going to fill out this information. On Friday, I gave you a very simple way of writing this information down. And I'll tell you, like, if you want to stick with that, if that's easier for you, you certainly can. And it's just, I put x, I put y, and I put all the 5 variables up there. The only thing that changed is I called this delta s instead. And the reason why is because, as we saw a second ago, that delta s is that arrow, whereas this guy is the x and this guy is the y. Sorry, people online. That's the x and that's the y right there. Okay? Now, your other way that you can do this information is this, okay? You don't have to do it both ways. You pick which way is easiest for you. Probably tomorrow, I'm going to kind of talk to you guys a little bit and see what generally everybody likes, and we will stick with whichever method you guys, most of you find to be the easiest. But when you do the information yourself, even if it's not what everybody else wants, you do whatever's easiest for you. Here's the thing. What is true of both of these two velocities in that column, always with projectile motion? It's the same, right? It's going to be the same. Whatever that velocity x is going to be the same. Why is it the same? Where velocity in the x doesn't move. Why? Correct. Acceleration in the x is 0 meters per second squared. We talked about this a little bit last chapter in 1D kinematics. I could write all 3 pieces of this information up here. Is that different information? So what a lot of people will do there is basically, instead of writing all 3 of these, they'll consolidate it. As a matter of fact, they won't write x and y anymore. Okay? And they will still sort of use 2 columns. But in the first column, they just write velocity in the x. They don't write vi, vf. They don't write a because it all means the same thing. Okay? Towards the bottom, instead of delta s, they'll write delta x because that's what it is. And then there's not these two columns because there doesn't need to be. And time, you kind of move it a little bit more towards the middle. Why do we move time a little bit more towards the middle? Because it's the same in both columns. So I don't write it twice, I just write it once. Now over in the y side, you still would write VIY, VFY, acceleration, time is the same, so we leave it there, and we write delta y, okay? I will tell you, when I first started doing physics, okay, I would have definitely been over here, was probably the easiest because it's the easiest to set up. It's almost exactly like last chapter. As I have done physics over the years, I generally tend, like if I'm doing this personally myself, I'm right over here, okay? Because there's a little bit less to write, it's a little bit more efficient. But again, I'll let you decide that kind of tomorrow. But right now, I'll come back over to this column and fill this in as we figure it out. So let's switching colors here real quick. Let's go to purple for this particular problem. What do we know? What do we know in this column of data about the car leading the table? VIY is 0. How come?
Because it initially starts with an acceleration and then velocity before it just kind of went out.
So I'm going to write that as 0 meters per second y hat. And if I were in your shoes listening to me, I would probably still think that the x hats and the y hats feel very like, it's dumb. Why are you doing them? I can figure this out. I guarantee, I think that as we continue in this chapter, you will see it a little bit more and a little bit more, especially as problems get a little more complicated. But for right now, just humor me. All right, what else you got?
Acceleration is negative g for y.
Negative g for y, and of course for the x, we already got done saying this, it's 0. Meters per second squared, x hat. What else do we know?
We have the delta s for both sides. Do you want to convert it?
Oh, not delta s for both sides. Don't say that. Okay. We know, to try to get the right language to do this, we know delta x and delta y, the components of it. Okay. So I imagine you converted feet to meters, 6.5 feet. There's 3.28 feet in 1 meter, so that's what, almost 2, a little bit less? 1.98 meters. Okay, where's that going to go? You can kind of see in my picture, yeah, like I laid delta x right across that 6.5 feet. That's how much it changes in the x. So yeah, this should be 1.98 meters x hat. And what else do we know? Delta y is? Not quite. It's not 0.868. Let me say that differently. It's not positive 0.868. It is negative. Now, the great news about this is, let's say you're doing this problem. Okay, let's say you're doing this problem and you don't put the negative 0.68. Now, for starters, let's talk about what you said happened if you say positive 0.868 and why it matters. You're saying the car leaves the table and then flings up into the air about 86.8 centimeters. Now, obviously we don't expect that to happen, yes? The great thing about physics is if you do the math correctly, the math will tell you that you are going to get an undefined number. As long as you don't just punch in like what you feel it should be, but punch in what it actually is, the math will tell you it's undefined, which lets you know, yeah, I've done something wrong. I should not be ending up with an undefined in this particular case if it's a real situation. And you can go back to the beginning and search for that negative. Be wary, as we've always discussed last chapter, about magic math. Like, oh, it's not supposed to be negative. Erase, 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 erase. You better have a good reason. You better know the reason why, because if I catch magic math, I'm going to take off a lot of points for that. Okay. You should go back and figure out why. Now, the question is, what are we looking for here? Yes, I said how fast I threw it down. Now, some key vocabulary as we continue in this chapter. If I ask you how fast, I am actually asking speed, which is a scalar. Okay? Now, oftentimes, though, I will ask for velocity being a vector. We'll talk a little bit more about that at the end. But ultimately, yeah, we need to go find this velocity in the x right here. Let's erase this for right now. We'll come back to this, like I said, tomorrow. All right. As you look at this, here's how you should see it. I got 3 variables over in the y side. Since it's accelerating, I know I'm using kinematics. Do I have enough information to solve stuff over there? Yes, I do. I'm going to take a step away from that and say, hey, over here, I got a bunch of information. Nope, you actually only have one piece of information here. What is it? You only know delta x. Because, if you'll remember, if this is 0, what is the equation for a constant velocity? What's the equation for a constant velocity? Displacement over time. So do you have enough information right now to solve for velocity in the x? Nope, but what easy information do you have in the y that's going to help us out? Yeah, we can go find the time in the y-axis. Now, I kind of breezed through this at the end of Friday, so let's talk about things that you're going to need to change about your equations now that we're in 2D. It's not a ton. All the kinematic equations stay pretty much exactly the same. There are just some very important things that you need to highlight, or you will make a lot of mistakes and take a lot more longer on this. So I'm going to write down the wrong thing first. This is what you would have used last chapter to get time. Why? Because that's a variable, that's a variable, that's a variable. I'm trying to find time. I'm missing VF. This is the one that's missing VF. So what will you say now instead of this chapter? Well, it's all entirely the same. The main things that you need to highlight are this. Number 1, that is not delta x. That's delta y. Okay? Number 2, velocities are your big thing that are split up into components. So to say velocity initial is like, oh, well, I know it's traveling, so it must not be 0. But this is not velocity initial in this equation. This is velocity initial in the y. There is technically one more thing that I will not require, but there's a problem later to make sure you understand this. Okay? Technically speaking, there should also be a component on the y right there. Now, the reason it doesn't matter yet is that when we do stuff in projectile motion, how much of acceleration is on the y? All of it. It's kind of inferred. Now, if you'll remember, though, here's how you technically calculate how much acceleration is on the y. This is my vector, 9.8 meters per second squared. The way I get how much is on the x and the y is trig. You really probably don't need to do the trig because it's easy trig. How much of that's on the x? On the x, you can skip it again. The x is 0, aka that's where I get my 0 from. And how much of it's on the y? Negative 9.1, yeah, all negative 100%. So it's negative 9.8 in that particular case. But there is a problem later this chapter. There's a problem later this chapter where it says, hey, we're going to go to a weird planet. And on this weird planet, gravity is down and to the left. Sorry, down and to the right. Okay? What's going to happen here? Well, in this case, is the acceleration entirely along the y? No. And how would you calculate it? Trig. But would acceleration in the x be 0? No. So you're going to want that component on this guy. And you're going to want to know that when you go to the x over here, it is not going to be constant, and you'll have to use kinematics in that particular case. It's actually arguably not that hard of a problem once you understand kind of the nuts and bolts of where this comes together. But going back here, like I said a second ago, you don't have to put that y right now. Let's go ahead and fill in this information and finish the problem. All right, don't plug in zeros. Don't plug in numbers unless there's a 0. Is there a 0? Yes. What is it? VIY, and that's 0. So I multiply, getting delta t, I multiply both sides by 2. I get 2 times delta y over a. Square root gives me delta t. Plugging my numbers in, I get 2 times negative 0.868 meters divided by acceleration is negative g square root. Right here, by the way, is where you would screw up if you had left that positive, because you'll notice you would have ended up with a negative under the square root, which would tell you, hey, this is a no-go, this is not okay. So that would let you know you need to fix that. I think it's like 0.42 seconds. What is it? 0.43? Sorry, that's 4 point. Yeah, okay. Let's just go 0.42. If you do it slightly off of that, that's completely fine. Okay, what is that? What does that represent? What is that measurement? The time to what? So it's the whole time, but I want to be very particular about this so you understand. We used the y to calculate this time. Meaning, if I had a toy truck that I flung off the side, and while I flung it off the side, I had another toy truck that I dropped, once again, which would hit the ground first. So the best way to understand this is that basically both cars stay in the air 0.42 seconds, right? It's how long it's falling is kind of the correct answer. But while it's falling, it's also traveling in the x, which is why it ends up specifically where it does. That being said, okay, here's your equation for constant velocity, although we are going to make one small change. Your equation is velocity equals delta x over delta t. You might have recalled from last chapter, I regularly had that as delta x equals v times delta t. I really don't care if you do this algebra in your head going back and forth. It's not that hard. The only thing I'm going to ask you to change about this is there is a component on that velocity of x. That is the velocity in the x. And of course here, delta x should be 1.98 meters divided by 0.42 seconds, and you should end up with a little less than 2.5. I got 2.4 and change. What do you got? Am I wrong? No, not 2.5. Sorry. No. I'm wrong. Less than 5. So 4.7, 4.8. 4.7. Cool. Give me another decimal on that. 4.71. Okay. Now, I'm going to do something here, okay, that really matters for what we're going to talk about next. This is technically an x component. Okay. Now, ultimately, if you're doing this problem yourself, you would not need to get this specific. You could leave it at 4.71 or 4.70. I don't know exactly what it is. Okay. You can leave it, and it's fine. It's fine. It's fine. But I want to talk about this real fast because it's going to matter with what comes next. Technically, the correct final velocity is 4.71 meters per second x hat plus 0 meters per second y hat. And you can see that this is a dumb way to list this particular velocity. Like, nobody really much understands this. And also, it's way faster to just do this. 4.71 meters per second at 0 degrees. Or instead of even saying at 0 degrees, you could substitute it by just saying horizontally, which we sort of already knew. Yes? My point in that is this. Our final answer is not this column. It is technically, switching to pink now, maybe, this, the combination of both of them. And I highlight that because now we're going to go to the back half of this problem that is maybe not as easy. The first question was, how fast does this car leave the table? Okay. The next question was, how fast does the car hit the ground? You come back over to my picture. Oops. We are trying to find this. Now, here's the truth. This guy right here, here's how you have to look at it. You have to look at it as some of it is moving horizontally, and some of it is moving vertically. And I'm going to try to label these so you can see where these numbers actually fall in the picture, in your mental picture. What is this right here? This horizontal line up there. The delta x. It is an x, but not the delta. What is this particular guy right here? Notice that it's on this triangle, right? This is velocity in the x. Do you already know what that number is? Yes. If I'm not mistaken, you just calculated it to be about 4.71. But if I ask you, or if any normal human being asks you how fast this hits the ground, do you think normal, non-physicsy people give a living crap how much it's going in the x and how much it's going in the y? No. Which part of the triangle are people always asking for if they want to know how fast something's going? They want the hypotenuse. Now, you and I now know, can you skip straight to the hypotenuse without knowing the individual pieces? No, you can't. You have to know both of those pieces. We know this piece now. What is that part of the triangle? Well, if that's velocity final, and this is velocity in the x. By the way, why doesn't this say velocity final in the x? Because the velocity is not changing, so we don't need to specify initial or final. That being said, what is this part right over here? That's velocity final in the y. So to get that, we can do absolutely anything we want to get that column right there. As a matter of fact, if I ask how fast it hits the ground, I'm asking for the total of this right here. You all right? Mm-hmm. I know it's not easy. Spain our drones on and the whatnot, but let's see if we can stay focused a little bit. Here we go. So you can use whatever the heck equation you want. What equation you want to use? Let's use the easiest one. Fine. That is not the easy one. I'm going to say this is the easy one. Velocity final equals velocity initial plus acceleration times time. Certainly the other one should get you the exact same answer. I would argue this is a little bit easier, but I did that equation wrong. What do I need to add this chapter? What's that? This should be velocity final in the y equals velocity initial in the y plus acceleration times time. Don't plug in numbers unless there's a zero. Is there a zero? What's the zero? Velocity initial in the y is 0. Acceleration is negative g. Time was, what did you say, 0.42? So you should end up with, if I remember correctly from last hour, it's negative 4.12 meters per second y hat. So this is why these hats matter. I'm going to call my shot right now on the final test of this chapter. I'm going to tell you exactly what one of the problems is going to be. And despite telling you this, based on my last 15 years of teaching and calling my shot as we do the problem for the very first time, half of you, or hopefully not, hopefully that's not the case, hopefully this isn't, but usually half of you are still going to mess this up. I will tell you right now that on the final test there will be a problem. It's meant to be a simple problem, an easy problem from the very beginning. An object gets thrown horizontally, and it'll tell you how fast. I'll say it's thrown horizontally at 3 feet, and it's like a foot and a half in the air, so they're a meter and a half in the air. How fast does it hit the ground? I will ask this exact question. I will tell you right now where most people will stop. Right here. They will stop right here after calculating this. Is this how fast it hits the ground? This is how fast a car would hit the ground if I dropped it. If I just let it go, that's how fast it would hit the ground. This is how fast it's going in the y. In the x, it's going, what did he say, 4.8 something, 4.7, so it's at 4.71. So, out of this triangle, I've already asked, what part do people usually want to know? The hypotenuse. Based on really basic trig, what very simple thing do you now have to do to find it? Pythagorean theorem, and yet still people will mess this up. Now, let's talk about a few things here. Here's the equation technically that it should look like. I know a squared plus b squared equals c squared. If you want to use that, that's fine, but here it is. Okay. A squared, velocity in the x squared, plus b squared, velocity final in the y squared, square root the whole thing is actually how fast it's going. So this is simply going to be 4.71 meters per second x hat squared plus negative 4.12 meters per second y hat squared. Square the whole thing. You should end up at about 5 and change. 4.71 squared plus 4. I'm sorry, 8 to get above 6. Yep, 6.26 is correct. Now, there are a bunch of things that I could actually ask you about this. The first thing that I could ask you is I could say what I just did. I could say how fast does it hit the ground. If I ever use the words how fast, I'm asking for speed. On speed, you're done. I could also directly ask you for speed. What speed does the object hit the ground? This is the exact same thing. You're done. The final question I could ask that separates a little bit is I could say what velocity does it hit the ground at? And if I ask for velocity, what's different between that and speed? Direction. So how on earth, I'm not going to do it right now because I think you can figure it out, but looking at this picture, what very simple thing do I need to do to give direction to that arrow? I would need to know what this angle is right here. And how would I find that angle if I had two sides of a triangle? Inverse tangent, yes, trig. Inverse tangent is going to give it to you. Y is a little bit smaller than the x, so I'm going to guess it's below 40, it's less than 45 degrees. You're, of course, looking at this, going to definitely get a negative angle because it's in the fourth quadrant, right? So this is probably going to be, so your final answer, if I asked for velocity, sorry, if I asked for speed or how fast, it would just be 6.26. If I asked for what's the final velocity, the correct answer would be 6.26 at probably negative like 42 degrees or something like that. What is it?
Negative 41.21.
There you go, negative 41 degrees. Yeah, it's no big deal. And we're not worried about that. All right, how you doing? All right, we're going to move on past this. This is the basics of all simple kinematics. You should be good to go on that particular assignment if you're working ahead. I think that is due actually on Wednesday, so make sure you're practicing that sooner rather than later. I'm going to give you another quick thing to talk about in your group while I pass back the quizzes. Please make sure you're staying focused on this as we continue, though. I got two major things to finish before we go. All right, so when we started this chapter, I talked about a bullet fired and a bullet dropped. Let's say this exact example shows up on a test. While I think that all of you know, I want to make sure that you can have the right language for this. Why do these? Of course, the result is they hit the ground at the same time. Why? What is the reason that they hit the ground at the same time? That's part of it, but there's more details than that. Meaning, like, okay, let's say, to counter that, here's my next example that I'm going to give, and they would not land at the same time. The next example I'm going to do in just a second is, what if instead the bullet is fired not horizontally, and I drop a bullet right next to it? Do both of these have the exact same gravity on them?
Yes.
Yes, they do. Gravity still affects them both the same once it's out of the gun. We are, by the way, assuming once it's out of the gun. So, even though they have the same gravity, these are not going to land at the same time. So coming back up here, why then, what do we need to add to? Yes?
They both have the same acceleration and the same initial velocity of light.
And there's one more thing you need to add, and there's one more thing you need to add to that. You're right there. Yes, that is true. They have the same acceleration. They have the same velocity initial in the y, and one more thing.
Same distance to the ground.
Correct. Meaning, and this is the simpler way to say this, if you look at this, they have the same essentially components in the y. Velocity initial in the y for the bullet dropped is 0. Acceleration is negative g, and delta y, I'm going to make up some number here. I was using negative h the other day. Let's say it's 1.5 meters in the air. So negative 1.5 meters. And the bullet dropped over here. Its initial in the y is 0. And its acceleration is negative g, and its delta y is negative 1.5. Now, we know now that if you have three variables, kinematics, that are the same, is everything else exactly the same? Yes. So simply put, the reason why they hit the ground at the same time is they have the exact same components in the y. Cool? So let's come down here to this situation. Obviously, they don't. But let's say the bullet was fired at 100 meters per second at an angle of 2 degrees. Now, this guy's going to stay entirely in the y. We're not going to go on the x. We're either going to, but simply put, we can't drop it and get it to land at the same time. Which one should land at the same time? Land first now. Dropped or fired? The one dropped. Correct. So the question is, what should I do to the bullet dropped so that it does land at the same time?
Or, sorry, add initial velocity.
Yeah, I'm going to say that differently, but yes, throw the ball. Throw the thing. Should I throw it up or down?
Up.
Should throw it up. Agreed. So the question, you have all the information you need now. In your group, try to figure out how fast do you have to throw this bullet over here so that it does land at the exact same time. Discuss. Colin.
I like that.
this is drama. Let's just wait for this. We haven't even gotten.
Oh, I was scared.
She was over here.
Gotta go worse.
Last night.
How do you run your line out?
Guys, make sure we're staying focused on the question at hand. I know that there's this. You guys have all the time in the world after this. All right, what's the answer? What's the answer? Okay, what is different about this scenario versus the other scenario? It's at an angle, so you just turn it into a triangle. Basically, simply put, what direction is the bullet going that keeps it from hitting first? It's going up. Do you have the capabilities of figuring out how much this is going up? What simple thing do you need to do to figure out how much this is going up? Sine. 100 sine of 2 degrees. Yes? And what do you end up with?
3.49.
That's less than I pushed the truck a second ago. So that means I could throw a bullet up in the air and it would land at the same time as a bullet fired at essentially 220 miles an hour? Yes. Why don't I have to throw it very hard?
Because it's not very good.
It's not traveling very much in the Y. Let's look at another example, and then I'll hand out that other quiz, and then we'll be done for the day. Imagine, if you will, there's a hill. Apparently it's a Mario hill. And on that hill, here's a person, and they're going to throw a bunch of objects up into the air. A bunch of balls all at the same time. They're going to go all over every sort of which way. And I'm going to draw up on the board for you their initial velocities, not displacements, not just how fast they're going at the very beginning. So let's say this one here is A, this one here is B, let's go, this here is C, this here is D, horizontally we'll throw E, and a little bit right down here, this is F. Now, my terrible hand drawing aside, please keep it with a grain of salt on exactly what you think the right answer is. But simply put, you should be able to look at this and answer a handful of easy to hard questions. Let's start with an easy question. Which object is going the fastest? It's definitely B, yes. B is going the fastest, yeah. Actually, I want to redraw one of these because I want to talk about something a little bit different here. I'm going to redraw D here. Okay, so let's go. Okay, which is the slowest? F. Okay, let's start with a harder question. Let's go into a harder question for you and your group to discuss. Two of these will hit the ground at the exact same time. Which ones are they and why? Two of these will hit the ground at the exact same time. Which ones are they and why? I'll try to redraw it over here too, not on the board here. So I can...
No.
Well, then ask the question, child. That's why we're doing it.
Are there any?
I have no issue. Listen, child, by the way, does not refer to you individually or long term. It defines that as a childlike idea. I don't know, but apparently I'm already supposed to before going into challenging physics content. Ask it. Why? Which one? What's your question?
No.
Do you ask which one is why? Which one is the fastest? No. Okay. All right. Let's do this. Let's talk about a handful up here. Let's go. A and D. Which one do you see as faster? It's kind of close. I recognize that. But the A is faster. Okay. Which one will hit the ground first?
D.
Why? How do you know?
Because it's closer to the ground.
It's It's not quite right what I'm looking for. You're
It's lower
there-ish, because remember, these
Lower
are,
delta.
all of these were launched from the exact same height.
It's got a lower delta Y.
It's not delta y. Let's make sure we do the right thing, because all of these are velocities.
Oh, sorry.
It's got a lower initial velocity in the y. Maybe you guys already know the answer to this, so I apologize. Maybe I'm drawing this out. Which two vectors do hit the ground at the same time? C and D. Why?
Because Y.
So if you're not seeing it, probably what you're trying to do is leave them as the arrows that they are. The way you have to look at this is you have to look at their components. The reason why A will hit the ground after D is because of this component right here. It doesn't give a crap what's happening in the X whatsoever. The reason why C and D will hit the ground at the same time is they have the exact same Y component. Now, what's D going to do different than C?
Go further.
Go further, because it's going more in the X in the same amount of time. Now, you might notice that possibly, I didn't do it perfectly over here, but A and C have pretty much the same X component, which means that if they were fired at the same time, here's what it would look like. They would basically stay on top of each other in the X because they're traveling just as fast as one another in the X. The difference in this case is, since C right here has a smaller Y component, it's not going to be in the air nearly as long as A in this particular time right here. You have to look at these in terms of their components. Last example I'll give you, and then I'll be done. Apologies, by the way, for the baseball example. If you're not a baseball person, I will use a lot of different sports throughout here. But for right now, I'm gonna stick with baseball because it's what I know. You go to a baseball game, you might hear the following phrase: "Well, that ball's not going anywhere. It's hit too high." Now, somebody not understanding, like, that's a dumb sentence. They hit it really fast. Since they hit it really fast, we want it to go high. That's an idiotic thing. Why is it, given what we just talked about, why you don't want to hit it at a very high angle? Yep. Is it going to stay in the air a very long time?
Yeah.
Is it going to go much of anywhere, though, while that's going on? What is the ideal angle to hit a ball at to get it to go the furthest? 45. We'll talk mathematically a little bit more later on. Why on earth wouldn't 60 be better? 60, will 60 keep it in the air longer? Absolutely, it will be in the air longer. So why is 60 still worse than 45? Because the X is that much smaller, and so you're not traveling very far while you're up in the air. By the way, we'll do this math a little bit later on. The complementary of the angle will always land at the same spot. 60 degrees and 30 degrees will land at the exact same location. 30 degrees, of course, not being in the air nearly as long, but much faster while that is going on, and vice versa, of course, for the ball that is up in the air. All right, pass back the rest of the quizzes, and then you guys are done for the day. Julian, I do not have your graphic addition quiz. Yes, please. Yeah, vector addition quiz is in the basket, Juliet. There we go. Just do the quiz. What's that? Yeah, just email me and you just do another sheet of paper.
Yeah, because I didn't make a really stupid mistake, and
Yeah.
that was my foundation.
Yes.
I wasn't even supposed to drop mine for I got the wrong unit. I don't know how.
Say that again.
I don't know what the context. I just don't understand. And another one I don't know how I just don't understand.
So should we do this?
I just didn't. It wasn't written down.
Yes.
So that was also my.
Oh,
Yeah,
okay.
that makes sense. Yeah, that was.
Melissa. Oh, sorry, down.